Chapter 22 is going to extend our discussion of Chapter 21. We're going to be talking about Gauss's law. And you'll find that there are limited uses of Gauss's law, but it is a very powerful law when you can use them. So for a little background information, one of Maxwell's equations for electrostatics that was actually simplified by a gentleman whose last name is Heaviside, is the divergence of the electric field is equal to the charge density, rho of C, over epsilon naught. Now, since the charge density is related to a volume, I could take and do a triple integral through the volume of my divergence, and I would have a differential electric field as a function of volume, and that's going to equal the triple integral of volume for the charge density divided by epsilon naught times the differential volume. So let's evaluate this side of the equation first. And if I'm taking a charge density, which is just charge per volume, and I'm integrating over that volume, then the total result is just going to be the total charge inside that volume. And then that's going to be divided by epsilon naught. Now on the right hand side, what we're going to find is we can use what's called the divergence theorem. And it basically changes a volume integral into a surface integral. So we designate that by an integral symbol with a circle, which means this is actually a double integral because it's a surface integral. And it's going to be the electric field dot product with the differential area. And this is Gauss's law. Now we're going to find why we have limited uses when we start breaking this down. But Gauss's law is a very interesting and useful, as I stated, law. So in this chapter, we're going to look at the definition of electric flux, then we'll actually look at Gauss's law, and some examples. And then we'll talk about some applications along with that. So this is really a short chapter, but we'll be using this just because it, like I said, it does simplify things in very specific instances.